Morning. So day 4, lecture over chapter 3, energy and matter. Before we get started, I just want to announce that anybody that hasn't done assignments or turned in any assignments by Sunday midnight, so Monday when I come in or when I get on and check, if you don't have any grades at that point, I'm going to assume that you're not attending class and you'll be dropped from the course. That's a requirement we have as teachers, so if you don't show up, we have to drop you. It affects financial aid, and so it'll save them money or cost you money. So make sure you're doing your assignments. That's how I know if you're showing up or not. We do have a lab today. You'll have 3 worksheets to do, 3 experiments to do. 2 of them are very similar. The other is density, which we covered last lecture. So after today's lecture, you'll be able to do everything in there. And I'll probably go through and do one of them with you just to get you on the right path. All right. So let's get into today's lecture. We're finally getting to some chemistry. All right, so chapter 3, matter and energy. You want to go through and read a lot of useful information. It also gives some examples that will help you remember these things. So matter is anything that has mass, occupies space. All right, go over all these vocabulary words. Make sure you know what they are. So a pure substance is fixed, definite composition, meaning that everything in it is the same. All right. Now, it could either be an element or a compound. So an element means that the substance all contains the same type of atoms, right? An atom is the smallest particle that matter can be broken down into. Hydrogen, helium, carbon, oxygen, these are all different kind of elements. And so if it's all the same atom, same type of atom, then that is just an element. If it's a mixture of atoms, say of different types of atoms, say water, for example, has hydrogen and oxygen, but all water is the same. All water is H2O. So that would be a compound, right? So when we're talking about compounds, we also have to talk about mixtures. Okay, so a mixture it's not a compound, but a mixture is different in that there are different types of molecules in there. So not only do they have different atoms, but they have different structures, probably different properties, okay, within the same mixture. All right. And when we talk about mixtures, we talk about homogeneous and heterogeneous mixtures. So the way to think about a homogeneous and a heterogeneous mixture, well, first let me back up. So we have states of matter. All right, we talked about matter being anything that occupies space and has mass, but there are 3 different states of matter, and you should all already know this, but gas, liquid, solid. Okay, so a solid is something that has a defined shape and defined volume. Is that right? Defined shape and volume, yes. Okay, and so the way that's different is liquid has a defined volume but not a defined shape. If I pour a glass of water, the water moves to fit the shape of the glass. If it was solid, it wouldn't do that. Say ice, the ice just falls in the bottom, rattles around. It's still the same shape, size, until it melts. Okay, so and then a gas, if I were to put a gas in that same cup, it would expand to fill the entire cup. All right, so it has no definite volume and no definite shape, right? So solid, definite shape and volume, always stays the same size. Liquid always stays the same size, but it can move. Gas expands to fill the space, so it doesn't stay the same size, and it moves. So that's how you can think about that in terms, you shouldn't have any problem distinguishing between a gas, liquid, or solid. All right, so now back to the mixtures that we were talking about. So Back up here under heterogeneous and homogeneous mixtures. So the way I like to think about this is the states of matter. That's why I wanted to bring up the states of matter. Thought I had a picture for y'all. I guess I don't. But so if we're talking about say sugar water, all right. So if or sugar in your tea. So if the tea is cold and I put the sugar in there, the sugar doesn't dissolve. It melts to the bottom, or it falls to the bottom, and I can see a difference in state, right? I can see the solid sugar particles down at the bottom, but then I also know that some of it dissolved into the solution. So that will be a heterogeneous mixture, meaning it contains both solid and liquid of different compounds and substances, right? So a homogeneous mixture would be if my tea were hot, all right? And I put the sugar in there, there's no ice, the sugar all dissolves into the mixture, and I can't see any difference between the sugar and the tea, all right? It's all the same. So that would be a homogeneous mixture. And several examples, thinking about, say, salt water. I think the book mentions salt water. If you were to take a glass of salt water and you see some sand in there, then that would be a heterogeneous mixture because there's a difference in liquid and solid states. And then if I just had the salt water, filtered out the sand, right, left with just the water, that would be a homogeneous mixture. Even though it has gold, silver, and probably some organisms and some other stuff in there, it's not visible, and so you can't see the difference. That makes it a homogeneous mixture. All right, so let's keep moving. When we're talking about the states of matter, they can undergo changes, right? If I boil water, then the liquid becomes a gas, okay? And if I freeze water, then the liquid becomes a solid. So these are some of the physical properties. When we go back to your text, so physical properties might be the color, shape, melting point, boiling point, physical state, which is what I just mentioned. And so when you're thinking about trying to determine which is a physical or chemical property, I would think about it in terms of the state of matter, right? Because a lot of the things that will confuse you, some of the physical properties are obvious, right? The color, the shape, the texture, stuff like that. But when you start thinking about changes in state, it can get confusing. So here's an example. So a chemical change would change the nature of the compound, the chemical properties, or even the molecule itself. Okay, so let's compare, say, boiling water with burning wood. Okay, so if I were to boil water, all right, and I can catch my steam in a little vessel, right, and then cool it back down, what's going to happen? My steam will turn back into water. Okay, so that's not a chemical change, that is a physical change. I've only gone from liquid to gas and then back from gas to liquid. Okay, so boiling water is an example of a physical change, a physical property change. All right, but now if I think about burning wood, all right, so same principle. I burn the wood. Wood is made of hydrocarbons, carbon and hydrogen. So I burn the wood and I catch the smoke this time. Instead of catching steam, I catch smoke. All right, and I hold that smoke in my vessel. When I cool it down, is it going to become wood again? It won't. Okay, so that has been a chemical change. We have changed the structure of the hydrocarbons that were in the wood, and they won't return to that state. So chemical change versus physical change. That's that. I'll probably add some videos as well, but you will have some of this on your Mastering Chemistry homework. Okay, let's keep on rolling. All right, temperature. Okay, so I mentioned this yesterday, I think, but we are going to want to do some practice with temperature conversions, because we use temperature for everything. It has a relationship with volume, pressure, mole value. We'll use temperature in most equations in chemistry. So let me bring up my iPad and let's do a couple practice real quick. So let's start. What if my temperature was 212 degrees Fahrenheit? Okay. And we typically in the United States use Fahrenheit as temperatures, but around the world they'll use Celsius. That's what we're talking about, English versus metric. So for all our assignments, you're definitely going to want to use Celsius. There are equations that use Kelvin, but a degree change in Kelvin is the same as a degree change in Celsius. A degree change in Kelvin is the same as a degree change in Celsius. Yes. So when you're talking about changes in temperature, like the difference between 270 Kelvin and 200 Kelvin is the same as the difference between 70 Celsius and 0 Celsius. So those are interchangeable if you're just talking about delta T, which is delta stands for change in mathematics. All right. So back to the problem. So say I have 212 degrees Fahrenheit and I want to get to Celsius. Okay, so my equation is TF equals 1.8 TC plus 32. Okay, so now if I want to solve for Fahrenheit, I need to start to move. Let's fill in our degree value. All right, it was 1.8 TC plus 32, right? Now I want to subtract 32 from both sides. So 212 minus 32 equals 1.8 TC. Divide both sides by 1.8. That leaves me with 212 minus 32 over 1.8 equals TC. Let's move that over here just a little bit. Okay, so again, 212 minus 32 over 1.8 equals TC, right? And I'll do that on my calculator. If I can find it. All right, 212 minus 32. So I like to separate I may have said this already, I like to separate it just so I don't have to worry about order of operations, right? So sometimes these scientific calculators, you have to put in the parentheses in the right way, and I did minus, not divide, sorry. 180 divided by 1.8 equals 100. Right, so 212 degrees Fahrenheit equals 100 degrees Celsius. All right, now that's important because the boiling point of water is 212 degrees Fahrenheit and 100 degrees Celsius. All right, so the Celsius scale was set up based on the boiling point and freezing point of water. Right, at 0 degrees Celsius, water freezes, going down, and at 100 degrees it boils, going up. So that's how the Celsius scale was set up. All right, so if I was going to go from, let's do one from Celsius to Fahrenheit. So say, I think the average body temp is 37 degrees Celsius. All right. And then we said that, let me take this back. Okay, so 37 degrees Celsius equals what temperature Fahrenheit? All right, so let's start with our equation. We say that TF equals 1.8 TC plus 32. Okay, so this time we have the TC value. We don't have the TF value. So let's just plug it in, and you can just do the math in this form. So that makes it easy enough. TF, sorry about that, equals 1.8 times 37 plus 32. All right, let's do our math. And if we do it right, the body temp at 37 degrees Celsius, we assume is like 98.6 Fahrenheit. Let's do my calculator and clear. Okay, so 1.8 times 37. Like I said, go ahead and separate that. Plus 32. Oh, didn't add it. 66.6 plus 32. 98.6. All right. So that's how you go back and forth from Celsius to Fahrenheit. And for Kelvin, simple enough, you just add 273 to whatever the Celsius value is. Okay, so Celsius plus 273 equals Kelvin. All right. You'll have some of those on your Master in Chemistry as well, and you also need to use, you might need to use these for the labs this afternoon. Yeah. Okay, so moving right along, we are in kinetic and potential energy. Okay, so kinetic energy is the energy that is created by motion. Okay, so anything that is moving has a mass and it can hit something, that's the kinetic energy that it has when it's moving. So I like to think about, say, a bullet. All right. So as a bullet moves through the air, it carries a lot of kinetic energy. All right, and can hurt somebody, obviously, but another thing like a baseball or a football, anything that's moving has kinetic energy. All right. Potential energy is the energy that exists from its position. So say a roller coaster at the top of a hill, right? While I'm sitting at the top of that hill, I have several forms of potential energy stacked up, right? There is a tension on the chain that drags me along, right? It wants to pull, but it's not letting me pull as much as I want. So there's like a tension. Think about that. Think about like a slingshot. Okay, the slingshot, when it's stretched, it has all this energy tied up in those bands, right? And when I let go of those bands, the potential energy is transferred into kinetic and it throws it forward. All right, so that's how potential and kinetic work. Back to the roller coaster. Let me pull that back up. So another way that potential energy exists is its space, its position, relative to any number of things. So a roller coaster sits way above the ground, right? So gravity is a force. All right, it pulls you to the ground. So the fact that I'm sitting 200 feet in the air, I have a lot of potential energy, right? If I were to jump off that roller coaster, I'd just slap fall, right? And that'd be a lot of kinetic energy. It came from the potential energy of my mass being so high above the ground, all right? There is a force pushing down against me. I resist that force. Therefore, I have potential energy. Same with the resistance we were talking about on the chains for the roller coaster, or the resistance on the bands for the slingshot. Okay, so the potential energy is something that's stored, and when it begins to move, that's when it becomes kinetic energy. All right. Let's see what else. Need to mention some more about that. Oh yeah, kinetic energy and potential energy. So when we talk about these energies in terms of chemistry, we're talking about them in terms of the atoms. All right. So this is what I mean. The kinetic energy of an atom is measured as heat. Okay. Heat is the energy associated with the motion of particles. So I said that kinetic energy is the movement, is the energy associated with the movement. So all these particles, if you remember from your college chemistry courses or physics courses, all atoms are made of neutrons, protons, and electrons. Okay, now the electrons, protons and neutrons stay in the middle, in the nucleus, and they kind of hold tight, but the electrons are moving around the outside really fast, faster than the eye can see, faster than we can even detect in some cases. So it's moving so fast. Now, how fast they actually move is an indication of the heat or the kinetic energy of that molecule, of that atom. All right, when you start getting into molecules where you have multiple atoms, you have a whole series of movements. All right, so the heat is essentially just how fast those things are bouncing around in there. If I apply heat, all those electrons start moving a lot faster. All right, they start bouncing off of walls, bouncing off of each other, and that's when we start getting temperature increase. All right, so now the potential energy is the energy that's stored within the molecule itself. So the electrons, they have a natural energy that they contain, right? They're charged, and they have potential energy from resistance and magnetism, right? A positive and a negative wants to pull together, but if my bond holds that electron from going away, I've just stored a little bit of potential energy. Okay, if a carbon is bonded to a hydrogen, there is some potential energy in that bond, and when I go to break it, say burning wood or something, there's energy released. Okay, so potential energy and kinetic energy, you think about it in terms of the real world like a bullet and a slingshot, but in terms of atoms, it is the movement of electrons and then the storage of energy within those bonds between the atoms. Okay, so potential and kinetic. Kinetic, we just said, was the heat. Kinetic energy in a molecule is the heat, and we measure this unit of energy or heat in terms of joule. All right, another word you'll know is calories, right? When we eat food, you consume calories. When you run, you burn calories. Well, those are all forms of energy. All right, they talk about eating good foods versus bad foods. All right, there's good energy and there's bad energy. What makes it good and bad is how it breaks down in your body. All right, so like carbohydrates and proteins break down in different ways. Okay, and provide different amounts of energy, different kinds of energy even. So calorie, the ones that you see on your food products and stuff, that is actually a kilocalorie, which would be 1,000 of the small calories. All right, so you got the conversions here. You're going to want to do that, want to practice this, and we're going to do some problems using all these later. So there is a conversion between a calorie and a joule. It's 4.184 joules equals 1 small calorie, right? Kilocalorie is written with a capital C. Just do it here. I guess it says on the next page. Yeah, so a kilocalorie is written, there it is, with a big C, and it is equal to 1,000 of the little calories with a little c. All right. This is a good little side article about carbon dioxide and global warming, right? We talked about how molecules kind of bounce off each other, and that's what creates heat. So that's kind of what's going on in the environment. That's a good article. Y'all to read that. Energy values. Okay, so this is kind of getting into what we might be doing in the lab today. This box here at the top of the screen is a calorimeter, okay? And we use this to determine the heat exchange when we combust products or foods or any number of things. We just burn it up and we can tell how much energy was lost, how much energy was in that substance or whatever we burned up based on the temperature change in the water. And there's an equation. We know how the energy associated with changes in temperature for water, and so we can kind of back calculate and figure out how much energy was in the food or the molecule that we combusted in the chamber. Okay, so, and this will kind of go into detail about what's kind of going on. There's some good practice problems here. You might want to use the book to help go over those before you jump into mastering chemistry. Okay, so now I said that we know how much energy it takes to change the temperature of water, okay? So some of these terms that we're going to use to describe these things, these characteristics are, one, specific heat, right? Specific heat is the amount of energy that it takes to raise 1 gram of water by 1 degree Celsius. Okay, so if I look at my equation here, I'm going to see that. The amount of energy, right, 1 calorie, or 4.184 joules, to raise 1 gram of water by 1 degree Celsius. Okay, so make sure you're saying it the right way and setting it up in your equation the right way. The amount of energy per, when I say per, remember to put your division in there. And so if I say miles per hour, miles on top, per hour on the bottom. So the per is like your break, all right? So try to say that when you're going, like density is grams per milliliter. So grams per line milliliter, all right? That's how I think of setting up my equations, word problems and stuff like that. So specific heat, the amount of energy per 1 gram and 1 degree Celsius. All right. So you'll use that equation. Another interesting point to point out, so let me go back to this calorimeter. So we just said that the specific heat of water is the amount of energy it takes to raise 1 gram of water by 1 degree Celsius, okay? So if I know how much water is in this calorimeter, and I know what the temperature change was, and I know that 1 calorie is equal to 1 gram changing by 1 degree, I could set this up so that I can determine how much energy was gained by the water, right? Because the temperature in the water is going to go up if I burn something in the calorimeter. So equally, the energy gained by the water is also the energy lost by the substance that we burned. So that's how we know exactly how much energy was in that combustion chamber. All right, the amount of energy that the water gained is the same amount of energy that the combustion chamber lost. All right, that's called the law of conservation of energy. Remember, we talked about laws. It's always true. All right, so back down, we are at specific heat. Let's keep rolling. Changes of state, we talked about that, right? Well, they are terms that you're going to want to know to identify these changes, okay? So if you look right here in your book, you'll see that we have sublimation, deposition, condensation, vaporization, melting, freezing. Most of these you already know just from life, right? Vaporization is like boiling it off. Condensation is when the water comes back from gas form. So you think about condensation on your glass. That water comes from the atmosphere. It cools down around the cold glass and deposits the condensation on the outside. So that's water that's coming from the environment. It condensates on the outside of your glass. It turns from a gas back into a liquid because it's been cooled. All right. Melting, freezing, that's obvious enough. If I have a piece of ice, it's a solid, I melt it, becomes a liquid. Vice versa, I have a glass of water, put it in the freezer, freezes as it gets colder, freezing. Now, deposition and sublimation are something that you won't see as often, but it does happen. And if we were doing real, like in-person labs, you get to see it. But it's really cool, actually. So sublimation is when a solid goes straight into a gas. It doesn't have a liquid form. And like I said, it's really dry ice. Dry ice is a good example, right? It doesn't ever form water. As soon as it starts to melt, just evaporates. So that's kind of that would be dry ice. That would be sublimation, excuse me. And then deposition would be the opposite. That's like me making dry ice from a gas. Okay, like I said, those are not as prevalent, but you do need to know those terms. Yeah. So melting point. The melting point is the temperature at which a substance actually melts. Freezing point is the temperature at which a substance actually freezes. All right. The heat of fusion and the heat of vaporization. Okay. Yeah. So the heat of fusion is the energy that must be added to convert exactly 1 gram of solid to liquid at the melting point. So energy per 1 gram solid. Okay, so the heat of fusion is the energy it takes for me to transfer something from a solid to a liquid, and it's expressed as an energy over gram. All right, and remember, you can flip this so you can use them in your equations depending on what you're solving for. We will probably do these labs next week. I want to touch on mole values and stuff before we get into this. But yeah, heat of fusion, heat of vaporization, these are just simple mathematical formulas you can use basically in the same way that we've been using specific heat. It's a certain number of energy that it takes to convert a gram of a substance. All right. So this will talk about sublimation, deposition, evaporation, condensation. Heat of vaporization is the same of heat of fusion, except for instead of going from a solid to a liquid, we're going from a liquid to a gas. All right. So we're hitting the boiling point. All right. So try to keep them in line like that, right? The heat of fusion is the point at which a substance melts. The heat of vaporization is the point at which the heat of vaporization is the energy required to make it boil. Okay, let me say that one more time. Heat of fusion is the energy required to make a substance melt. Heat of vaporization is the energy required to make it boil. 1 gram in particular. All right. So, practice problems. These are pretty much straightforward. I will do some work in the lab with calorimeter. Just to make sure that we are on the, like I said, I may wait on that until we cover moles, because I want to make sure that we're not doing anything you're not familiar with. Okay? So one of your labs, I think will have a chart, something like this. You'll heat up the substance and record the temperature as the heat is changed. Okay? Notice right here that the water and steam both exist right here on this plane, and then right here at the freezing point, water and ice both exist on that plane. So there's like a transition state when you can technically say that both states of matter are present. All right. Now in real life, this happens fairly quickly if you're applying heat or reducing heat fast enough. Okay, some practice problems. I definitely recommend looking over that. Let the book kind of walk you through them. All right. Cool. Yeah, I'd say vocabulary is definitely important on this one. Um, I don't like this chart as much. Doesn't really have much good flow to it. But so I'm gonna try to add some videos, some practice. You will have some mastering chemistry problems. I doubt I'll do as much because we're going to do a lot of this in lab. I doubt I'll do as many problems as I did for the last two sections. Okay, so yeah, make sure you read your text and get on your homework, and I'll see y'all in lab in a little while.